Good day, my name is Kubis Strigelski, and today I'll be covering Learning Area 8, which is the risk of a portfolio, and this is the second part of a two-part series of lectures on the topic. If you'd like to contact me with any questions, you are most welcome to do so. My email address is on the slide before you right now, and I'm also available for telephonic conversations on Wednesdays between 10 and 12 o'clock. And my telephone number is there for your reference. So this lecture will cover the concept of diversification, and we will put everything together that we've learned and discuss correlation, diversification, and returns. So this is a follow-on from the previous lecture in which we developed measures to describe the expected return on a portfolio and also a measure of risk on a portfolio in the form of the standard deviation. What you should be able to do after this lecture is to understand the concept of diversification and also understand how diversification can reduce the risk of a portfolio. So one of the central concepts that we discussed in the previous lecture was correlation, and diversification is the reason why correlation is important. So first, let's start off with this idea as to how risk can be reduced through diversification. Well, the textbook definition states that risk can be reduced by combining assets that have a negatively or weakly correlated. So by combining assets that are negatively correlated, and this is what is important, overall variability is reduced. Remember, what was important or how risk was measured was the divergence from our expected outcome. So what we are looking at is the divergence between the actual outcome that we have, so for example, a return in a given period, and the expected outcome, the return that we're expecting for a given period or over a given period of time. So diversification is therefore the reduction of risk by combining assets in a portfolio with different correlations. And below you see two assets. So you see asset F and asset G. And what we are going to do is we're going to combine these two assets into a portfolio consisting of F and G. And in this diagram, what you have is you have the expected returns for these assets. So this is an expected return for asset F. Then we have an expected return for asset G, which corresponds to the R bar there, and obviously an expected return for the portfolio. Now, as you can see, this line here shows how returns on asset F increase and how they decrease. So for example, here, what we have is a peak, and here we have a trough, to use an economic terminology. And for asset G, that is the same case. So what we have is we first have a trough, and then we have a peak. Now, if you look at assets F and G, returns move in opposite directions. So for example, as the returns on asset F increase, okay, what happens is that the returns on asset G decrease. Okay. Alternatively, as the returns on asset F decrease, the returns on asset G increase. So essentially what we have is we have perfectly negatively correlated assets. So as the one goes up, or as the returns on asset F go up, the returns on asset G decrease. Now what we want to do is we want to combine these two assets in a portfolio. And what is the result? Well, the result, as you can see here in this diagram, is that the variability, in other words, the deviation from our expected return, which is measured by the distance between the line, the orange line that I am placing dots on, and the expected return decreases relative to the deviation that you see for actual observations and expected returns for asset F and asset G. So what we have done is we've combined asset F and we've combined asset G, and we've reduced the variability as the two move in opposite directions, and that is seen in the portfolio of asset F and G. So whereas asset F and asset G have greater variability individually, combining these two assets in a portfolio results in reduced variability. So the moral of the story, or the lesson here, is that as long as assets are either imperfectly correlated or negatively correlated, risk will decrease. We'll be able to reduce the variability of a portfolio by combining assets with such characteristics. And the lower the correlation between the two assets, the greater the potential for diversification. And the potential for diversification is highest when you have a situation of perfectly negatively correlated assets. So perhaps the best way of demonstrating how diversification works in practice and how correlation comes into it Perhaps what we can do is we can look at an example. So what you have is you have three assets. You have asset X, you have asset Y, and you have asset Z. Okay, and you have returns that are given for a period of 5 years, starting in 2010, going to 2014. And what we want to do is we want to construct two portfolios, portfolio X and Y, and portfolio X and Z. So what is it that we need to do? Well, the very first step is to calculate the expected returns on each portfolio, and we do that next. So in order to demonstrate how diversification works and how correlation comes into play, what I will do is I'll go through workings from the previous for the example on the previous slide, where we have three assets, and those are assets X, Y, and Z, and we formulate two portfolios, which portfolio X and Y, and X and Z, where you have 50% of stock X and 50% of stock Y, or asset X and asset Y in portfolio XY, and then 50% of asset X and 50% of asset Z in portfolio XZ. So the very first thing that we need to do is we need to calculate the expected returns. So we have the expected returns for 2010, and here we have the weighting for asset X, which in the portfolio, which is 50%, and the return on asset X in 2010. Next, what we have is we again have the weighting, so it is the sum of the weighted returns of the constituents. So here that 0.5 corresponds to a weighting of asset X in the portfolio, and 16% represents the return in 2010 on asset Y. And the expected return for 2010 on portfolio X and Y, the combination of assets X and Y, is therefore 12%. And the same procedure holds for 2011. So again, it is the weighted return, the weighted returns of the constituents on the portfolio. So again, that's 50% of the return on asset X and 50% of the return on asset Y. And that again gives us an expected return for 2011 of 12%. The same holds for 2012, 2013, and 2014. So now what we need to do is calculate the expected value of returns over the entire period, and what we find is the mean or the average of the returns over the 5 years. So that's 12% plus 12% plus 12% plus 12% plus 12%. Okay, those are the values that we are using, divided by the number of periods. That is the number of years, and that is 5. And what you find is that the expected return on portfolio X and Y from 2010 2014 is 12%. So that's the average return we get, or expected return we get each year. Then let's move on to the next portfolio and calculate the expected returns in each year, and hence the overall expected return. So we have portfolio X or Z, and again in 2010 half of the portfolio consists of or comprises of asset X, and that is 8%. That's the return we have in 2010 on asset X, and on asset Z we have also a return of 8%, and it comprises half of the portfolio. So the expected return on the portfolio in 2010 with those weightings and returns is then 8%. The same procedure applies for 2011, so we have 10%, then we have 12% for 2012, for 2013 we have 14%, and then we have for 2014 we have 16%. Again, we need to calculate the expected return or the overall expected return for these years. So what we do is we find the average. So again, as you can see, these are the values for the individual years, where you have 8% for 2010, you have 10% for 2011, 12% for 2012, 14% for 2013, and 16% for 2014. Again, what you do is you then find the mean, and we find that the expected value of returns from 2010 to 2014 is 12%. So now we are well on our way to demonstrating the concept of diversification. However, before we do so, what we still need to do is we still need to find the standard deviation. In other words, we need to find what the risk of each portfolio is. So now that we've calculated the expected returns on each portfolio over the years, what we need to do is we need to estimate or calculate the standard deviation, which measures the risk. And for those that don't remember, here is the formula for the standard deviation. If you want a more elaborate explanation, please refer to the first part of the lectures series on the risk of a portfolio. So let's start with our standard deviation for portfolio X and Y. So applying that formula, what we find is that the standard deviation is 0. Okay. Now, why is that the case? Because there is no deviation of the outcomes observed in each year and the expected outcome. So the expected outcome is 12%, and that corresponds to R bar in our formula, and that we calculated in the previous slide. However, in 2010, the actual or the outcome for the year is 12%. For 2011, it is also 12%. And for 2012 it is 12%, and so on for 2013 and 2014. So we have outcomes of 12%. Our expected returns for each year are 12%, and the expected return over the period is the overall expected return is 12%. So hence there is no deviation, there's no variability, there's no divergence of the outcomes in each year and the overall expected outcome, which is also 12%. So hence our standard deviation is then 0. Okay, and we'll see why that happens to be the case for this specific portfolio, although the expected returns for both portfolios are 12. Okay, yet the standard deviations differ, as you will see now. So let's look at portfolio XZ. So again, we apply the formula, and here you have the 8%, so that is the expected return in 2010. Here you have 10%, which is the expected return in 2011. Then you have the expected return for 2012, 2013, and 2014. The overall expected return is 12%. So again, we see that here, and that is what corresponds to R bar. Okay, so note in this instance that outcomes that we observe in each year differ from the expected outcome overall, which is at 12%. So for example, in 2010, we have an expected return on the portfolio in that specific year of 8%. However, we expect an outcome of 12%. So hence what we have is we have a divergence, we have a deviation. So what that implies is that in this instance we have a higher standard deviation. And that is indeed the case. The standard deviation for on portfolio XZ turns out to be 3.16%. So what is interesting on this slide, that although both portfolios have the same return, okay, in other words, the expected return over those 5 years from 2010 to 2014 is 12%. The standard deviation, in other words, the measure of risk, differs. It is 0 for portfolio XY and it is 3.16% for portfolio XZ. Now, why is that the case? Well, that is what we'll see in the on the next slide. So what we now have done is we've calculated the expected returns on portfolio X and Y and portfolio X and Z. And what we have found is that in both instances, the expected value of returns is 12%. However, what differs across these two portfolios is the standard deviation. So the standard deviation for portfolio X and Y is 0, and the standard deviation for portfolio X and Z is 3.16%. And what this is telling us is that portfolio X and Z is more risky than portfolio XY. Now, why is that the case? So if you look at asset X and asset Y, which are then combined to form portfolio XY, asset X increases, or the returns on asset X increase as the returns on asset Y decrease. So essentially what is happening is that the increases in returns on asset X are offset by the decreases in returns on asset Y. And the result is that we have a lower deviation from our expected outcome. So as you can see, although that asset X is increasing, asset Y is decreasing, and hence this results in our expected return for each year staying at 12%. Now let's look at our other portfolio, portfolio XZ. So as X increases, what happens is the return on asset Z also increases. Okay. So what is happening is that although our expected return is 12%, our returns for each individual year are increasing. So we have a higher deviation, in other words, a higher risk of our observed returns in each year relative to our expected outcome, which is measured by the expected return. Okay. Now, because assets X and Y are moving in opposite direction, we have negative correlation, and that negative correlation is what is responsible for lowering and eliminating the deviation of the returns observed in each year relative to our expected return. Whereas for assets X and Y, what we have is we have perfect positive correlation. So asset X moves together with asset Z. As the returns on asset X increase, so do the returns on asset Z. And what happens in this instance is because they are moving together, because there is no offsetting effect, because they are perfectly correlated, or specifically perfectly positive correlated, what happens is that there is a deviation from the expected outcome as we move along. So in other words, there's a high level of variability. As you can see, for example, in 2010, the expected value of the portfolio is 8%. It then increases to 10%, to 12%, to 14%, and then to 16% finally in 2014. So there is a high level of variability, and it is for this reason, because there's no offsetting effect as we would see with assets X and Y, okay, because assets X and Z are positively correlated, there's a greater variability in the form of a greater deviation in each year from our expected value of the portfolio over these 5 years. So hence, because we can combine assets X and Y, we can have the same expected outcome of 12%, however with a lower risk, because we reduce the variability of the portfolio as a result of perfectly negative correlated assets. So what are the important outcomes to note from the previous slide? So first of all, as returns on X increase, returns on Y decrease. So what is happening is that any gains on X are offset by decreases on asset Y. And the result is that in each year we have an expected return of 12%, and that does not deviate from the expected value of portfolio returns, which is also 12%. So hence what happens is, because the two move in opposite directions, we are able to offset any variability that might arise. So that is where we're seeing diversification. On the other hand, as returns on X increase, the returns on Z also increase. And what happens is that the movement together, or the perfectly positive correlation that we see here, results in a deviation from our expected value of portfolio returns of 12% over the individual years. So hence what we have is we have a higher standard deviation, we have high level of risk for our portfolio XZ. So now, although I've already mentioned that in passing on this slide, what we can say is that assets X and Y are negatively correlated because they move in opposite directions, whereas assets X and Z are positively correlated because they move in the same direction. And we've already answered this. Which portfolio would have the lowest risk? That would be portfolio X and Y, because of the lowest variability in expected returns for each year, which arise as a result of negative correlation observed. And that is how you see diversification in action. Risk can be reduced by combining assets that are able to offset any increases or decreases in returns. Okay. In other words, assets that are negatively correlated or have a weak positive correlation. So on this slide, what we have is we have a reiteration of what we've stated before and a brief summary. So we can have the following correlations. Okay. In other words, assets can be perfectly positively correlated. They move together. They move together one for one almost. Well, one for one if we have perfect correlation. They can be uncorrelated, or they can be perfectly negatively correlated. What that means is that they move in completely opposite directions. Of course, they're in between. So the relationship might not be perfect, but it might not be imperfect. In other words, that there isn't perfect positive correlation, but the assets are also not uncorrelated. In other words, there is some level of correlation. So if you have two assets, let's say asset A and B, as asset A moves up, so returns on asset A increase, the returns on asset B also increase, but not to the same extent. So for example, if returns on asset A increase by 2%, the returns on asset B will increase by 0.5%, 0.5% in other words. So that is a correlation that is not perfect, but it is positive nevertheless. So there are, in other words, in-betweens. It is not only, we are not only dealing with situations where correlation is perfectly positive, perfectly negative, or there is no correlation at all. There are in-betweens. So what we can do is by combining stocks which are weakly correlated or negatively correlated, we can reduce the risk of a portfolio. And this is what we call diversification. So now this is another summary that you will see in your textbook. So here what we have is we have expected returns, and we have a given level of risk for assets P and Q. If we start with the ranges of returns corresponding to correlation, so we have perfectly positive correlation, uncorrelated returns, and we have perfectly negative correlation. What happens is that the range of returns remains the same. However, the greatest reductions in risk can be achieved if you have assets that are perfectly negatively correlated. Okay, so as you can see here, you can reduce the level of risk to 0 if you have perfectly negatively correlated returns. On the other hand, you can get some kind of reduction if there's no correlation. Okay, so whereas the lowest level of risk is on asset P in this instance, okay, so that is what we see here. Okay, we can have a level of risk that is even lower if we have uncorrelated assets in our portfolio. Okay, so in this instance, the risk on the portfolio can drop below 3%. On the other hand, the level of risk, if we have perfect correlation, will range between the level of risk on the individual assets. So for example, for asset P, it is again 3%. So this is where we see that 3% for asset P. On the other hand, on asset Q, the level of risk can be 8%. So we have this range of between 3 and 8%. So what is evident from this graph, or what is important about this diagram, not graph, diagram, my apologies, is that the greatest reduction in risk can be achieved if assets are perfectly negatively correlated. There can be somewhat of a reduction in risk through diversification if assets are uncorrelated or combined, okay, and you can have a level of risk that is lower than either level of risk for both assets. And if you have perfectly positive correlation, there is no reduction of risk. Okay, the range of risk will be between the risk that is attributable to both assets in your portfolio. So what is the outcome? Risk is potentially highest when assets are perfectly correlated. This is because two assets move together and hence losses are not offset and variability is not offset. Variability is highest in this instance. Okay, so that is the case here. Okay. Risk is lower when assets are uncorrelated. Although one asset may be negatively impacted by a shock, the other asset will not follow. Hence, the impact of a negative shock is not as severe, and hence, to some extent, okay, there is perhaps not maybe an offsetting effect, an offset of returns, but returns are less variable because they do not move together. Okay, so hence the deviations from the expected outcome in the form of expected returns is lower. Okay, now the final case is when we have perfectly negative correlated assets. This is when you can have the greatest reduction in risk, and this is because any shocks are offset. Any shocks to one asset are offset by the response of the other asset because they move in opposite directions. So variability is reduced the most when assets are perfectly negatively correlated. So the result is that the reduction in risk is greatest for perfectly negative correlated assets. And thank you. That brings us to the end of our two-part series on the risk of a portfolio. I look forward to hearing from you. My email address is restated on the slide before you. And I'm also available for telephonic consultations between 10 and 1200 hours on Wednesdays. Thank you, and I look forward to hearing from you.